Images from the James Webb Space Telescope. This one shows two galaxies swirling in a chaotic object right in the middle there.
In the depths of space, something extraordinary has been unveiled. The James Webb Space Telescope, our cosmic eye, has peered back in time to discover two of the most distant galaxies ever observed. These ancient cosmic giants formed just 300 million years after the Big Bang, shedding light on the universe's infancy. But what secrets do these galaxies hold? And how did the James Webb Telescope manage to spot them from such incredible distances? Join us as we dive into the incredible findings of the Webb Telescope, as it brings us closer to understanding the origins of our universe. In the vast expanse of our universe, the James Webb Space Telescope has turned its gaze towards the enigmatic epoch in cosmic history known as the Dark Ages. This period, veiled in mystery and largely unexplored, holds the key to understanding the early universe's evolution. What secrets do these cosmic Dark Ages harbor? And how does the JWST's recent discovery of two of the most distant galaxies ever seen challenge our understanding of this enigmatic era? The cosmic Dark Ages refer to a time after the Big Bang, estimated to be about 380,000 years post the universe's fiery inception, stretching up until the formation of the first stars, nearly 150 million to 1 billion years later. During this period, the universe was devoid of any luminous objects like stars or galaxies. It was a time when the cosmos was a vast expanse of darkness, filled with neutral hydrogen and helium gas. The only radiation emitted was in the form of the cosmic microwave background, or CMB, a relic from the Big Bang, which provides us with a snapshot of the universe at its infant stage. But with the James Webb Space Telescope unveiling ancient galaxies from this obscure era, could it be that the so-called Dark Ages of the universe were not as dark as we once thought? To answer this question, we first need to delve into the importance of this period. Understanding the Dark Ages is like piecing together the earliest chapters of the universe's story. It's the bridge between the universe's birth and the emergence of the first luminous objects. Understanding this era is crucial for piecing together the narrative of cosmic structure formation, the nature of the first stars and galaxies, and the processes that led to the universe becoming transparent to light. One of the most fascinating aspects of the Dark Ages is the process of reionization. Initially, the universe was opaque to ultraviolet light due to the abundance of neutral hydrogen atoms. However, as the first stars and galaxies began to form, their intense ultraviolet light started to break apart these hydrogen atoms in a process known as ionization. This epoch, known as the reionization era, is critical because it marked the universe's transition from opacity to transparency, allowing light to travel freely across the cosmos. But how did the first stars and galaxies form in this primordial darkness? The prevailing theory suggests that small fluctuations in the density of matter in the early universe led to the formation of the first structures. Over time, these overdensities, primarily composed of dark matter, attracted more matter through gravitational pull, eventually leading to the formation of stars and galaxies. These celestial objects started to illuminate the universe, bringing an end to the Dark Ages. JWST, with its unprecedented infrared sensitivity, is perfectly equipped to peer back into this cosmic epoch. But why is this so? Enter redshift, a key concept in modern astronomy that allows us to peer back into this epoch. This term refers to the phenomenon where light from distant objects in space is stretched, or shifted, towards the redder end of the electromagnetic spectrum because of the expansion of the universe. As galaxies move away from us, the light they emit is stretched, increasing its wavelength and shifting it towards red. The farther away a galaxy is, the faster it moves away from us, and the more its light is redshifted. But redshift is more than just a measure of distance. It's a window into the past. When we observe a galaxy with a high redshift, we are seeing it as it was billions of years ago, because the light from that galaxy has taken so long to reach us. This makes redshift an invaluable tool for exploring the cosmic Dark Ages. By observing galaxies with the highest redshifts, astronomers can study the universe during its infancy. Crucial to this mission is the James Webb Space Telescope, specifically designed to observe these high redshift galaxies which lie beyond the reach of current telescopes. The JWST's observations of high redshift galaxies are expected to answer key questions about the Dark Ages. For instance, what were the properties of the first stars? How quickly did galaxies form and evolve in the early universe? And how did these first stars and galaxies contribute to the Ryanization of the universe, ending the Dark Ages? Astoundingly, the JWST has unveiled what was once thought impossible: the sighting of two galaxies at a redshift so high, it propels us almost to the brink of the universe's infancy. These distant galaxies, known as Glass Z13 and Glass Z11, date back to 300 to 400 million years, which is about 100 million years earlier than anything previously identified. But what is the significance of these cosmic specters? And how do they revolutionize our perception of the early universe? The sheer distance of these galaxies from our planet is not their only astounding feature. Their size, structure, and composition tell a tale of a universe very different from the one we know today. Glass Z13 and Glass Z11, despite being observed in their infancy, are surprisingly large, hinting at a rapid growth rate. They defy our previous expectations of galaxy size in the early universe. But how big are they? While exact measurements are challenging due to their distance, initial observations suggest they are larger than what was thought possible for galaxies at such an early stage. This challenges our understanding of how quickly galaxies can form and grow after the Big Bang. The structure of these galaxies is another area of intrigue. Early galaxies are expected to be somewhat chaotic in their appearance, lacking the well-defined structures like spiral arms seen in more mature galaxies. These distant galaxies, however, show signs of having more structure than anticipated. This could mean that galaxies began to organize and form distinct structures earlier than we thought, opening new questions about the processes that drive galaxy formation and evolution. So these groundbreaking observations by the JWST are not just reshaping our view of the distant cosmos. They're also challenging foundational theories about the Big Bang and the subsequent evolution of the universe. The Big Bang theory, the cornerstone of modern cosmology, posits that the universe began as an infinitely dense point, approximately 13.8 billion years ago, which then rapidly expanded and cooled. This theory has been supported by substantial evidence, including the cosmic microwave background radiation and the distribution of galaxies. However, the discovery of galaxies like Glass Z13 and Glass Z11 by the JWST is compelling astronomers to reconsider aspects of this theory, particularly concerning the timeline of galaxy formation as previously mentioned. According to the Big Bang theory, the universe underwent a series of epochs, starting from a hot, dense state and transitioning through various stages, including the Dark Ages, reionization, and the formation of the first stars and galaxies. The recent discoveries suggest that galaxies formed much earlier than previously thought. This revelation potentially accelerates the timeline for galaxy formation, indicating that the processes that led to the creation of these structures were in place sooner after the Big Bang than our models had predicted. Furthermore, the applicability of physical laws in the earliest epochs of the universe is another area under scrutiny. Were the physical laws as we understand them today the same during the universe's infancy? The conditions immediately following the Big Bang were so extreme that they may have altered the behavior of fundamental forces and particles. The JWST's observations of the earliest galaxies and stars provide a unique laboratory for testing the laws of physics under these extreme conditions. By examining the light from these ancient celestial bodies, scientists can infer the physical processes at play and test whether our current physics models hold up in the high-energy environment of the early universe. This acceleration of galaxy formation also has implications for the understanding of dark matter and its role in the early universe. Dark matter, an enigmatic substance that does not emit, absorb, or reflect light, yet exerts a gravitational influence, has long been a subject of intrigue in astrophysics. It is thought to comprise about 27% of the universe's total mass and energy, but remains invisible and undetectable by traditional telescopes. Dark matter's elusive nature makes it one of the greatest cosmic mysteries. While we cannot see dark matter, we know of its existence due to its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Its gravitational pull is believed to be crucial in pulling together the gas necessary for the formation of the first stars and galaxies. This unseen matter acts as the scaffolding on which the visible parts of galaxies are built. Understanding how dark matter contributed to the formation of the earliest galaxies, like those observed by the JWST, is key to comprehending the universe's evolution. The role of dark matter in early galaxy formation is a topic of intense research. Current theories suggest that shortly after the Big Bang, dark matter began to clump together due to its gravitational attraction. These clumps, or halos of dark matter, provided the gravitational wells into which gas fell and began to form stars. But the existence of sizable galaxies like Glass Z13 and Glass Z11 so soon after the Big Bang suggests that dark matter structures might have formed and influenced baryonic matter, which is the matter that makes up stars, planets, and life, earlier than we have assumed. Understanding when these dark matter structures began to form is crucial, as it sets the timeline for the subsequent formation of stars and galaxies. The current theory suggests that shortly after the Big Bang, minute fluctuations in the density of the universe led to areas where dark matter was slightly more concentrated. Over time, these regions of higher density began to collapse under their own gravity, forming the first structures in the universe. The early formation of galaxies like Glass Z13 and Glass Z11 hints at a more rapid assembly of these dark matter structures than previously thought. This rapid assembly could have provided the necessary gravitational pull to gather gas and dust, leading to the formation of stars and galaxies at an accelerated pace. Moreover, the role of dark matter in the early universe extends beyond just the formation of galaxies. It also has implications for the way galaxies are distributed across the cosmos. The large-scale structure of the universe, which includes the vast filaments and voids that we observe today, is believed to have been sculpted by the distribution and behavior of dark matter. The presence of mature galaxies in the infant universe suggests that the process of structure formation, driven by dark matter, may have commenced sooner and proceeded more quickly than our models indicate. However, the exact nature of dark matter remains a puzzle. Various candidates have been proposed, including weakly interacting massive particles, axions, and sterile neutrinos, but none have been definitively detected. The JWST may contribute to our understanding of dark matter through indirect means. By studying the distribution and properties of the earliest galaxies and comparing them to the predictions of dark matter models, astronomers can test these theories and potentially narrow down the characteristics of dark matter. Furthermore, the JWST can study phenomena like gravitational lensing, where the light from distant objects is bent and magnified by the gravitational influence of dark matter. Observations of gravitational lensing can provide insights into the distribution and concentration of dark matter in galaxy clusters. By studying these gravitational lenses, the JWST can help to map the dark matter in these regions, providing critical information about its properties and behavior. In the narrative of cosmic evolution, the role of dark matter is just one of several enigmas challenging our understanding of the universe. Another perplexing issue is the antimatter problem, which raises questions about the fundamental nature of matter in the universe. According to the Big Bang theory, the universe should have created equal amounts of matter and antimatter. Yet the universe we observe today is predominantly composed of matter. What happened to the antimatter? This discrepancy poses a major puzzle for cosmologists. The JWST's deep space observations might offer clues by revealing the conditions of the early universe where matter overcame antimatter, potentially shedding light on this long-standing mystery. Going back to the two galaxies, their observation also raises questions about the nature of the first stars and galaxies. According to current theories, the first stars, known as population 3 stars, were massive, hot, and short-lived, significantly different from the stars we see in the current universe. These enigmatic stars were the universe's very first luminaries, lighting up the cosmic stage for the first time. They emerged from the primordial gas left over from the Big Bang, consisting mainly of hydrogen and helium, as heavier elements had not yet been formed. Population 3 stars are believed to have been giants compared to modern stars, possibly hundreds of times more massive than our Sun. Their massive size meant they burned their fuel quickly and fiercely, emitting copious amounts of ultraviolet light. This intense radiation played a crucial role in the early universe, impacting the formation of subsequent generations of stars and galaxies. But what makes these stars truly fascinating is their simplicity. Lacking heavy elements or metals, as astronomers refer to elements heavier than helium, these stars were fundamentally different in composition from later generations. This lack of metals affected not only their formation, but also their life cycle and death. Their demise, often through spectacular supernovae, seeded the universe with the first heavy elements, setting the stage for the complex chemistry that eventually led to planets, and even life. But as we delve deeper into the mysteries of these stars, it becomes clear that comprehending their true distances is an essential piece of the cosmic puzzle. The methodologies used to measure cosmic distances are as fascinating as they are varied, each method building upon the other like rungs on a ladder, aptly named the cosmic distance ladder. The first rung on this ladder is parallax, the apparent shift in position of a nearby star against a background of more distant stars, observed as Earth orbits the Sun. This method is akin to the way objects move relative to each other when viewed from different positions. Parallax is used for measuring distances to stars up to about 1,600 light-years from Earth, and provides the foundation for further distance measurements. Building on parallax, astronomers then use a technique called main sequence fitting. This method relies on the understanding that stars with similar properties, such as temperature, luminosity, and color, follow a predictable pattern in their life cycle, known as the main sequence. By comparing the observed brightness of a star with its expected luminosity based on its position on the main sequence, astronomers can estimate its distance. The next crucial method involves standard candles, objects whose luminosities are known. The most famous of these is the Cepheid variable, a type of star whose brightness changes in a predictable way. The relationship between the period of these changes and the star's intrinsic brightness allows astronomers to calculate its distance. Similarly, type Ia supernovae, explosive events at the end of a white dwarf's life, serve as another form of standard candle due to their consistent peak brightness. And finally, for galaxies far beyond the reach of Cepheids and supernovae, astronomers turn to redshift. These methods combined form the cosmic distance ladder, each step building upon the last to extend our reach further into the cosmos. By measuring cosmic distances, astronomers can piece together the structure of the universe, trace its expansion, and unravel the mysteries of its origin and evolution. Now that we've explored the foundations of our celestial knowledge through the cosmic distance ladder, let's turn our gaze toward the groundbreaking discoveries made possible by the James Webb Space Telescope. One of its most remarkable findings includes the detection of water in a main belt comet. This discovery is particularly intriguing as it challenges our understanding of water distribution in our solar system. Main belt comets, orbiting between Mars and Jupiter, were not traditionally considered prime candidates for holding significant amounts of water. The presence of water in this region hints at complex processes of migration and interaction among celestial bodies in the early solar system. This finding could have profound implications for our understanding of how water, a critical ingredient for life as we know it, was distributed and delivered to planets like Earth. Moreover, JWST has turned its gaze closer to home, providing stunning insights into Jupiter's atmosphere. The images and data collected reveal intricate details about the gas giant's weather systems, cloud formations, and auroras. These observations offer a new level of understanding of Jupiter's atmospheric dynamics and composition. The level of detail captured by JWST in Jupiter's atmosphere is unparalleled, showcasing swirling storms and winds, and even casting light on the mysterious processes happening in the planet's auroras. This closer look at our solar system's largest planet not only enhances our knowledge of Jupiter, but also improves our understanding of gas giants in general, which are common throughout the galaxy. Another area where JWST has made significant contributions is the detection of previously unknown features in the atmospheres of exoplanets. This particular observation was made possible by JWST's ability to analyze the transmission of starlight through an exoplanet's atmosphere, providing detailed information about its composition. One such exoplanet, known as K218b, has garnered significant attention. This exoplanet, which lies in the habitable zone of its star, has shown signs of water vapor in its atmosphere, a crucial ingredient for life as we know it. The discovery of water vapor in K218b's atmosphere is particularly striking because it suggests that the conditions on this exoplanet could be conducive to life. This finding opens up new possibilities in the search for habitable worlds and underscores the JWST's role as a pivotal tool in this quest. Thanks for watching this episode of Beyond Discovery. Don't miss the video you see on your screen, you won't believe it.